brief lecture because and easy to understand, because it's like we are repeating ourselves here, but with the generator case. So I'm going to talk a little bit about the generator. What are the main differences between the motor and the generator, and also the characteristics of the load and the generator, which is electrical load, of course, here. And by this, we're going to finish basically the DC machines side. So you can see here the separately excited machine, and it's the same exact circuit. I just want to highlight what will be the direction of current here. And we discussed maybe this, if you remember before. Now the direction of current is from the armature to the terminals. Why? Because we are generating electricity. So this is the output. And here is the input mechanical. It's separately excited. So IF has its own circuit, or the field circuit, field winding has its own circuit. And yeah, that's it. Nothing more to say here. In the motor case, if you remember, the current was in this direction from right to left. But in the generator case, it's from left to the right. So which voltage is larger here in this case? It's the EA. So if we write the KVL equation, it's going to be like this. VT, which is this terminal voltage, equal EA, armature voltage minus the voltage drop on this resistor. For the shunt generator, again, it's the same thing. The current will be from the armature to the terminals. This is the input here, and this is the output. So the IA will be from the armature to the terminals. IF, the same thing, is down, and IL will be the difference, again to the terminals. So not much again to say here. We are using the same exact equations that we are familiar with. The difference here will be that EA is larger, so it's going to be here minus instead of positive in the motor case. Also here, it's a little bit different because we are applying KCL. So IA will be the addition of IF plus IL. IF will be the voltage divided by R. Are we okay so far? I mean, is it clear to you the differences between the motor case and the generator case?
Yes.
Yes.
For the series DC generator, again, we are talking about the current from the armature to the terminals. So if we just analyze, it's going to be similar to what we did before, applying KVL equation. Of course, we have only one current in this circuit. The compound DC generators, as I mentioned before, this is for your information, and you need to know what are the connections of both the short shunt and the long shunt. And the short shunt is basically this one, the one below. This is when we connect the field in parallel with RA, similar to the shunt. But after that, we have the series field connected to both of them. For the long shunt, we connect the field in parallel with both the series and also the armature. Both can be either commutative compound or connection or differential compound. It depends. If you remember the meaning of the dots here, okay? So yes, let me just clear everything. If the dots are in these locations, it means that they are opposite. Sorry, they are the same thing in terms of current. So the current will enter this, the current will enter this, so same directions. So this is commutative compound. It means that the effect of the field parallel field and series field will be additive. If it is differential, meaning that the dot is here and after that the dot here, it means that they are opposite in terms of polarity. So the effect will be subtractive between them. And we're going to see at the end the behavior of each cumulative compound and differential compound. So each connection here, the short or the long, can be cumulative and can be also differential. The power of law, it's similar to the power of law that we learned before about DC motors, but for the generator case, as I mentioned again and again, it's about the direction. The input is mechanical, the output is electrical. So first we have the mechanical losses, and the mechanical input is torque omega. Then we have the developed power, which is torque omega equal EAIA. This is converted or developed. Then we have the losses, I square R losses, and terminal electrical output. Okay? Any question regarding this?
Clear.
Okay. So just revising a couple of equations also here and there. E, which is the voltage, but now it's the voltage generated. So we generate this voltage is equal K flux omega. Torque is equal K flux IA. This is IA. And we know that we can replace this with IF. Nothing new here. So this is when we replace flux with IF. So the load characteristics, if you remember in the motor case yesterday, I said if we are talking about the load in the motor, it's mechanical. So load characteristics meaning it means that we need to analyze the parameters of the mechanical load, which are torque and speed. So we studied the relation between them. If the torque is increasing, what will happen to the speed? So the load characteristic for the generator case, the output is electrical. So we're talking about voltage and current. So again, it's like we're studying the relation between the voltage and current. What will happen if the current is increasing from no load to full load condition, etc. So the load characteristic is the relation between voltage and current. One important also concept that I need to mention here, I didn't mention it with the motor, but I just want to mention it with the generator part. It's not a new part. You know this, which is BH curve. You remember the BH curve from the magnetic circuit, the magnetization curve? Well, remember that we are using also magnetic material inside the machine, meaning that, for example, in generating field from the field winding, we need to apply current, which is the field current. So when you increase the field current, you are generating magnetic field, but still, which is this. So when you increase the field current, you are generating MMF, and as a result, you are generating flux. But we know that this is not a linear relation. This will follow the BH curve, and you have the saturation region at certain point. So IF also, it has an impact in the generator case with the generated armature voltage. Meaning, in the generator, if you keep increasing IF, what will happen? Well, you are generating more magnetic field. More magnetic field, it means more voltage generated. Is it linear relation? No. If you keep increasing IF, you are generating more flux, you are generating more voltage. But at certain point, the flux will be saturated and the voltage also will be saturated. So it's the same relation, the BH curve applied also to the generator case between IF and EA, or between MMF and the flux. So these are using electrical quantities, these are using magnetic field quantity.
Doctor,
Mhm.
what is the reason behind this saturation?
It's a property of the material. تشبع الماتيريال تتشبع من المagnetic field، ما تقدر يعني ما في
No, I mean in the okay, this is in the magnetic circuit, but in the generator,
we
is
have
it the also?
yeah, remember that we have also in the generator, for example, the field winding, right?
Yes.
And this will generate flux. This winding is basically similar to the magnetic circuit that we learned before. So we have magnetic core also.
Okay.
Okay.
Doctor, doesn't it make more sense to plot the EA, the voltage, versus IA, the armature current?
Yeah, but you are here you wanna basically, this is if we are talking about load characteristics, yes. But here we are talking just about the relation between IF and EA, which is basically, it's like we are linking the relation between input applied to the field circuit and the output caused because of this flux. Okay. So no, the one that you control is IF. The one that it's an output, a result, is IA. So you want just to show the relation. What will happen if we increase the input, which is IF, to the output, which is EA? Okay.
Doctor,
Mm-hmm.
the load in the generator will be in the terminal.
Yes, that's correct.
Okay.
So similar also to what we did with the motor, if you remember, we measured the speed regulation, right? Which is speed no load minus speed full load divided by speed full load. In the generator case, we're talking about the load, which is electrical. So we should talk about voltage regulation, similar to what we did with the transformer. So the voltage regulation is basically the voltage no load, voltage full load divided by voltage full load. And it is represented using this equation, which is voltage no load, EA, voltage full load, VA, divided by VA. So in separately, for example, excited machine, the circuit is of the armature is like this, right? So if we have load, the voltage will be VA. So it is clear. What if we don't have load? This is open circuit. What will be the voltage? The voltage will be EA. Why? Because the current here will be equal to 0, right? So the same voltage here will be at the load. So that's why we are replacing voltage no load by EA in this equation. So yes, we can use voltage regulation to measure the performance of the output, the voltage. Also, we can calculate the energy efficiency, which is the power output divided by power input. Just very quick example here, although as I mentioned, it's similar to the examples that we solved before. A DC shunt generator, so we know the connection, it's shunt, has armature and field resistances of 0.2, 150. The generator supplies 10 kilowatt at 230. Find what is induced voltage, EE. So we know the connection, it's shunt. The resistance here is 0.2 and this is 150. We need to find EE, and the voltage here is 230. volt and the power supplied is 10 kilowatt. So the question here is find what is EE. So how we find this?
Find the field current first.
Yes, and we need, before we do that, we need to specify the directions of currents. And this
Yes.
is the main difference. I mean, if it is a motor, we do the directions of currents different. If it's a generator, we know that the current here will be
To the right.
from left to the right, yes. Okay? And yes, now we need just to analyze all the currents to find the voltage here. So first thing we can find what is IF. IF in this case will be the voltage, which is 230 divided by 150. So we find this. Can we find this?
Yes, we have the power and we have the voltage.
So we have the power 10 kilowatt. We have also the voltage 230. Can we find this? Yes, of course. It's KCL, right? Will be the IF plus IL. This one plus this one. Then can we find this EE? Yes, it's 230 plus IA 0.2. So nothing actually new here. I mean, once you draw the circuit, I know this is maybe the confusing part for you, which is mapping the values to the circuits here. Once you draw the circuit and specify the directions of currents based on the type of the generator of the machine, that's it. You are just analyzing very simple electric circuit. I'm not gonna solve this, but try to do it at home, because this is basically what we did last time with couple of examples. If you remember, I mentioned that this is before and after example, right? So you have case 1, you have case 2, and you can see here, for example, the parameters of the circuit and the rated values at no load. So this is case 1, no load. The terminal voltage is 240 volt. The field current is 1.25. And the speed is 1200 RPM. When the generator delivers rated current to a load at 240. So what do we mean by rated current? We're talking about 12 kilowatt, so which is rated power, rated current, rated power, same thing. And the voltage 240. Find EE and field. So you are required to find EE in this case.
They didn't specify shunt or compound or anything.
Separately excited.
Okay.
Which is the same analysis as the shunt, yeah, no difference. So how we solve this? We use the ratio, right? We can say that we have this equation EA is equal K IF omega, and here also EA K IF omega. So this is 1 1 1 1 1 1, and you just find the ratio. Okay, so this will be cancelled with this, and you can write this one as N1 N1. It's easy. I mean, it's the same as we did last time, so do it at home and make sure that you know how to find this and you know how to find this. It's a simple practice. It can be done at home. Okay?
Victor, the I field is the same for both cases?
Yes, yes. It's not mentioned specifically here, but it is the same.
That applies for the generator and the motor, or only generator?
This is separately excited, of course, and it depends on the connection, but separately excited, the field circuit is different than the armature, right? So IF, it is specified here to be 1.25, and there is external source for IF. And yes, you control this. So in the lab, you change this IF, right? So here it is specified to be 1.25 and it is fixed for both cases, no load or full load. Unless he's saying that the IF when there is load is different. And yes, if it is motor or generator, and it's the same case.
Doctor,
Yes.
the question is about shunt, not separately excited. IF will be different.
No. If it is shunt,
Yes.
might be different, yes.
Because
in the shunt-
in the first case, which is we have 1.25 current. After that, in the rated case, we have to find the current, which will be different.
yes, that's what I'm saying. It depends. For example, here he's saying that the voltage is 240 in both cases, right?
Yes.
So 240 no load, 240 full load, and this is, for example, 200. So IF here is the same because IF is always the voltage divided by the current. Okay.
Yes. I mean the armature current, not
The
field
armature
current.
will be different, of course, yes, because it's based on this current, whatever you have current here.
Yes. Could you just make that clarify to me in the separately excited circuit? I'm just a little bit confused.
Again,
Could you just explain it in the separately excited circuit? I'm just a little bit confused.
and the separately excited, as you can see here, the current you have IF separated from IA, which is in this direction. So IF is not related to the circuit at all. So you have no load, full load, it doesn't matter here. IF is the same.
Yes.
Because this is you apply it from another circuit. And imagine this is a battery and you are applying 100 volt here and you have RF here is fixed. So IF will be always the same. So what happened actually, and maybe this is what you did in the lab, you can increase this, you can control this, right? Because if you control this, you control the voltage generated here.
Yes, since it's parallel.
So if because if IF is 0, there is no flux, there is no EA or VA. But once you keep increasing this voltage, what will happen? You generate more, right? So this is a load characteristic, but for this specific problem, it is specified that the current is fixed. You're not changing anything in the circuit. Okay?
Okay.
But in analysis, you analyze, for example, the armature circuit to find the parameters here. For example, the question in the second part, find what is VF, what is this voltage? Well, you have the current IF, you have the value of resistor, so you analyze this circuit, which is simple circuit, current and Ohm's law. Okay? That's why it's called separated, because both circuits are separated. So if you need any parameter here, you analyze this circuit. If you need any parameter here, you analyze this circuit. Clear?
Clear, but isn't VF the same as 240 voltage?
No. Terminal voltage. No, terminal voltage, which is VA.
The direction different of
The direction of what? So this is VA, not VF. We're not mentioning actually VF in the question. We need to find it later, VF.
Isn't both of them parallel?
Again?
Isn't parallel?
You mean this voltage is in parallel with this voltage?
We have resistor. I'm sorry.
No, they are separated. This has nothing to do with this.
Yes, got it.
Completely different circuits.
Yes, thank you.
Okay. Again, this is another example, very simple example, similar to what we did before. It's about the ratio before and after 1 to just do it at home. There is no point of doing it. Usually, I solve half of the question and I leave the other half for you. So here, for example, you have 125 terminal voltage, field current of 2, speed of 1780. So 125, 2 amp IF, speed 1780. Calculate the generated voltage. So what is EA? When the field current is increased to, so here the field current is not the same, is increased to 2.5. You remember the discussion in the previous slide? So here you are increasing the field current. So yes, it's different, not the same. And just find EE. Again, it's the ratio. And again here, for example, the speed is different. It's now 165 and the field current is 275. Find again what's the voltage. So nothing new here. Just to go through some parameters or factors that can affect the voltage drop and the performance of the machine. And for example, the armature resistance drop, meaning that the voltage drop because of RA, because if we have a current in RA, this is a voltage drop. Brush contact drop, again, this we explained this in the motor case. So we have voltage drop because of the brushes. And it is usually 2 volt, but it should be mentioned in the problem. If it is not mentioned, no need to include it. Armature reaction, if you remember the armature reaction, I explained this yesterday. It's because of the current in the armature will generate a magnetic field that will weaken the net magnetic field inside the machine. So it's negative impact of the magnetic field generated from the armature. You need the magnetic field generated from the field, not the armature. Reduction of terminal voltage in self-excitation generator. This is because of self-excitation. Part of the current you lose it for the field. So this is normal. This is explanation of the armature reaction. I already explained this yesterday. And I said that this is the reaction between the magnetic field from the armature and the magnetic field from the field. The magnetic field from the armature because of the current in the armature. So if you have load, you have current in the armature and you have this reaction. The solution for this is to use compensating windings. So once you use compensating windings in the machine, it means that you are eliminating the effect or minimizing the effect of armature. We need just to go through some characteristics of some machines and see exactly what will happen if we increase the current, the load, to the voltage. This is a separately excited machine. And if the load current is 0, it means that there is no load. The terminal voltage is the same as EA. You agree? You remember this? So no current, EA, same as VT. If the machine is ideal, what will happen? If we increase the load current, it's the same voltage because it's ideal. There is no voltage drop. But the machines are not ideal. So you have this IARA drop. So if you increase the load current, now the voltage, terminal voltage will start to be less and less. And this is because this equation, right? If IA is increasing, VT will start to decrease. Another factor can contribute also, which is the armature reaction drop. So this is the dashed line here without considering the armature reaction. If you consider armature reaction, you will see that the voltage is somehow non-linearly dropping with the load current. And this is what you did in the lab, of course. You examined the behavior of machines when you have load, when you increase the field current, etc. So the separately excited machine, at no load, the terminal voltage will be the same as the armature voltage, but after that will start to decrease with the load current. For the shunt, it's almost the same. And I'm gonna go back almost the same as the separately excited. You have the effect of RA drop and also the effect of the armature reaction. Just to explain one characteristics of a shunt, let's imagine that you have a shunt generator and you want to start the shunt generator. How you can start shunt generator? This is a very practical concept. Well, the shunt generator, remember that the field is in parallel to the armature. And you need to generate voltage here. So how you generate voltage here if the field current is 0? Remember that you need magnetic field from the field. So imagine that this is a brand new machine generator and you are providing the mechanical input. So it is there. And you need to generate terminal voltage. How you do it? Because you need also magnetic field coming from here. And here the current is 0 because when you start the machine, the voltage is 0. So what do you think? How we can provide field current to this field winding?
Maybe using a battery.
Battery in
That's
the middle.
correct. Yes, couple of concepts here. One practical concept is to start the machine with battery. It's like we started as separately excited, and after that, when it runs, it shifts to shunt or self-excited. So one way is to bring a battery and just provide the current, and after that you disconnect the battery. Another way is to utilize the residual flux you have inside the machine. You remember the residual flux, the hysteresis loop? We said that even if you turn off the magnetic or the source for the magnetic circuit, you still have magnetic field inside the machine. So you utilize this small magnetic field. The field current will be small. The voltage will be small. So let's assume that this is 1, this is 10. So what will happen after that? We start to generate small voltage. And this small voltage now will contribute more to the field. So the field current will start to increase. If field current starts to increase, the voltage also will start to increase. Then the field current will start to increase. This is basically represented here, which is called the build-up characteristics of the shunt motor. You start with a small current, field current, either using battery or using the residual flux inside the machine. This small current will generate small magnetic field. This small magnetic field will generate small voltage. This small voltage now will generate more field current. And it's a loop. Okay? From IF, flux, voltage, after that more IF. And it goes on and on till you reach the rated voltage here. So this is called the build-up characteristic of the shunt generator. For the series, just to finish this part, for the series, again, the characteristic is a little bit different. Why? Because if there is no field current, if there is no load, it means that there is no field current. So if this is open circuit, there is no field, there is nothing here, and there is no voltage also generated, right? Because you don't have current in the field. But once you start to connect load, current now will start to flow and voltage will start to generate more. And this is the curve. It's a little bit different than others for the series generator. If you have 0 voltage, you have almost, why we have a small also voltage here? Why it's not completely 0?
Residual.
Yes, because of the residual flux you have inside the machine. Will always generate this small voltage. Even
Because
if
of
the
the
current...
losses.
Because
of the losses, this is the residual.
Yeah, it's basically losses. Yeah, it's basically losses inside the machine. Once you start to increase the load current, which is the same as the field current, the voltage will start to increase. And because of the drop of the resistors, since we have 2 resistors now, the voltage drop will be higher now, right? So that it's going to be sharp decrease because of this voltage drop. You remember that you have two resistors here. And if you add an armature reaction to the equation here, the decrease will be more with load current until you reach a point where it's like collapsing. So this is a collapse. What does that mean? It means that with more load current, you are reaching zero. So the slope is negative here. You are not increasing the voltage anymore. Actually, with more load current, you are decreasing the voltage you generate. So these are all the curves for all the generators. First, you have the shunt, which is the green one. So with more load current, you have less voltage. You have series, of course, shunt, it's similar to the separately excited. You have series, so you start with a small value, you increase, you keep increase till you start to decrease again. Then we have the compound generators. Compound generators can be almost anything. If it is cumulative, it's going to be more like the shunt. It depends what are the values. So you'll have like more additive effect, and it start to increase and after that decrease. If it is, sorry, I'm not sure. Differential, yeah, differential is highly decreasing nature. So it's gonna start to decrease from the start. Okay. And this is called the over compound because you are basically increasing the voltage. Flat, it means that it's almost a line. Under compound, it means that it's decreasing, which is the same as the shunt. So what's important here is that you know all the characteristics. I mean, if, for example, in the exam, if I point out to this and they say, what's the characteristic of this? Which type of machine? You should be able to know what type of machine. If I point to this and say, what's the type of machine here, the yellow line, you should know that this is the series machine. Okay? Any question regarding machines? So we are done with DC machines. And as I mentioned before, you need to understand both of them. It doesn't work if you understand one, the motor case, and you don't understand the generator, or the generator and you don't understand the motor. It's a package. You need to understand both of them. You need to understand for each type the basic concept, structure, and also the load characteristics. And of course, different equivalent circuits for DC machines. Next time, when we will meet on Saturday, we need to discuss, we will start to discuss AC machines. Remember that this is still DC. Now on Saturday, we'll start AC machines. Okay? So we'll see you inshallah Saturday, same time. Assalamu alaikum.